Welcome. I am Felicitas Schaefer and I'll be presenting our research on the impact of exceptional points on the reliability of thermoacoustic stability analysis. This work was carried out by me and co-workers at TU Munich. Thermoacoustic stability analysis is often carried out using eigenvalue analysis. For a given input, the thermoacoustic solver predicts the system eigenvalues. The system is rendered linearly stable if the eigenvalue growth rate is smaller than zero, indicating that the system oscillations are damped rather than amplified. However, stability analysis itself may not suffice to reliably predict the dynamics of the thermoacoustic systems, as these systems are highly sensitive to a large number of input parameters. This may cause the eigenvalue to shift to the unstable plane, even for small variations in the system parameters. This is especially problematic since parameters are always subject to uncertainties, that is, the operational conditions deviate from the nominal conditions due to stochastic fluctuations. In addition, parameter values in the thermoacoustic model are also uncertain. As a result, eigenvalue predictions are always subject to uncertainties. Predicting these uncertainties may get very costly as it usually involves evaluating the system for a large number of input samples. Uncertainty quantification methods therefore often rely on identifying a cheap surrogate model that replicates the system response over a range of input variables with significantly reduced computational effort. In the scope of this work, we want to look at uncertainty quantification at so-called exceptional points. Exceptional points are degenerate eigenvalues with only one eigenfunction. This means that at an exceptional point, two or more eigenvalues and their respective eigenfunctions coalesce. A characteristic property of exceptional points is that eigenvalue sensitivity becomes infinite in these points. We suspect that this also affects the standard deviation of eigenvalue predictions made for the corresponding eigenvalue. Furthermore, we asked ourselves whether surrogate models are still able to capture this very particular system behavior in the vicinity of exceptional points. So these are the 2 points we want to present today: surrogate models at the exceptional point and uncertainty propagation at the exceptional point. However, in order to have a closer look at exceptional points, we first need to identify the corresponding parameter setting. We therefore developed a new method that allows us to cheaply identify exceptional points in thermoacoustic systems. In our study, we considered a pre-mixed swirl combustor. To calculate the thermoacoustic modes, we employed a one-dimensional network model where the flame was represented by a finite impulse response. As design parameters, we selected the time lag tau c and the reflection coefficient at the chamber exit R out. In practice, tau c can be modified by changing the position of the swirler, whereas damping devices or the turbine working conditions directly affect the value of R out. From the eigenvalues obtained for the initial parameter settings, we select two eigenvalues, which we suspect may coalesce at an exceptional point. Our goal is now to tune the design parameters such that the two initially selected eigenvalues move towards each other and ultimately coalesce, resulting in an exceptional point. So let's have a closer look at our algorithm. In this picture, you can see the eigenvalue branches around the exceptional points for different values of the tuning parameters tau c and R out. As mentioned before, we start with two eigenvalues that are found for the initial system setup. We assume that the location of the exceptional point can be approximated by taking the mean of these two eigenvalues. Now that we know our guess, we need to find the corresponding system parameters, tau c and R out. To find these, we developed an efficient solver based on a joint theory, which is described in detail in our paper. Having found the values of our tuning parameters, we once again calculate our system eigenvalues. We get two eigenvalues, unless we are already at an exceptional point, as eigenvalue 1 has traveled from here to here, and eigenvalue 2 has traveled from here to here. From the new eigenvalues, we calculate our new approximation of the exceptional point. As you can see, we approach the actual value of the exceptional point swiftly, having only used 2 iterations so far. With this method of identifying exceptional points, we were able to firstly demonstrate the existence of an unstable exceptional point in the thermoacoustic spectrum for realistic parameter settings. Furthermore, the representation of our flame is much more realistic than what had been investigated in previous studies on exceptional points. In the next step, we investigated the impact of exceptional points on the identification of reliable surrogate models. We use Gaussian process approach to train surrogate models both for a simple eigenvalue and at the exceptional point. Here you can see how the GP model performed for a simple eigenvalue. The reference values obtained from the thermoacoustic solver are plotted over those obtained from the GP model. Clearly, the GP model is able to capture the system dynamics as all data points are located along the red 45-degree line. In contrast, the GP model performed very poorly at the exceptional point, even as we increased the number of training samples, which we can see as the data points are widely distributed along the 45-degree line. This failure of the surrogate model has 3 reasons. The most obvious of them is that the training data contains not one eigenvalue branch, but 2 around the exceptional point that cannot be generalized by only one function. However, the results only improved slightly when we pre-selected the training data such that they only contained data belonging to one eigenvalue branch, for example, the blue one shown here or the orange one shown here. To further explain this, we therefore plotted the frequencies and growth rates for the marked eigenvalue trajectories over the values of tau c. As you can see, the functions are not smooth at the exceptional point. This can also be observed for the remaining uncertain parameters. Yet, the GP model is based on a smooth ansatz function, which cannot reproduce this particular system behavior. This is the second reason why the GP model fails at the exceptional point. Lastly, the increased sensitivity in the immediate vicinity of the exceptional point accounts for an insufficient number of training samples around the exceptional point, which further impairs the quality of the surrogate model. For randomly drawn samples, we can clearly see a lack of samples in the areas around the exceptional point, which are here marked by the green circles. In summary, the 3 reasons why the GP model is not able to adequately capture the system behavior are the 2 different eigenvalue branches at the exceptional point, the ansatz function of the GP model that cannot capture the non-smooth behavior in the parameters, and the limited training data at the exceptional point due to the increased sensitivity. We therefore fell back to the more expensive Monte Carlo simulation to investigate uncertainty propagation at the exceptional point. The obtained PDFs for frequency and growth rate are shown here in blue. The black PDF was obtained for the simple eigenvalue shown earlier. As expected, the standard deviation is significantly larger at the exceptional point. This becomes even clearer when looking at the isolanes of the probability density, where the 10% isolane of the exceptional point encloses an area over 4 times the size of the one enclosed by the 10% isolane of the simple eigenvalue. In conclusion, we developed a new method of identifying exceptional points in thermoacoustic systems. We showed that these systems may feature metastable or even unstable exceptional points. We further used the identified exceptional point to study the effect of these eigenvalues on uncertainty and the process of uncertainty quantification. We found that classical methods of uncertainty quantification may fail at the exceptional point, as results obtained from surrogate models may be unreliable. This is especially critical because the effect of uncertainty is amplified in the vicinity of an exceptional point due to the increased eigenvalue sensitivity. Thank you for watching.